with SQL, and we'll be using MySQL. So as part of this sessions, we'll be using MySQL and try to understand what SQL is. So for these sessions, I would request you all to have MySQL software downloaded. That is what would be helpful in order to, run SQL queries on top of MySQL. It is pretty straightforward installation. I'll point out the links as well. From those links, downloading is pretty easy. Okay, so first thing is we'll try to understand what is the way in which storage has evolved, right? So we have something called as a Selectron tube. This was the first device that was found out in order to store some kind of storage. And this was about 4096 bits, hardly any bytes of data. I mean, in today's measuring capacity, if we were to look at it, it is very low. So Selectron tube was for something that we started using initially, or that was the first device that came up. That was not a commercial purpose, but that was something that people started experimenting on how do we store data onto a machine. So that was the Selectron tube that came up. It had some kind of an intense beam that was generated to a particular area, and that particular area used to have some kind of information stored in the form of bit. And that is essentially a Selectron tube. And then came what were called as punching cards. Punching cards are essentially something where we have a sheet of paper or a sheet of some material, not necessarily paper, but it is some material wherein there are certain holes that are being made, and it is about 80 columns. It has about 80 columns, and holes are made at places wherever we want to represent some information in every column, right? That is what was used as a punching card. As we go further, we'll try to understand more about it. And then came the magnetic drum memory based storage. This was big cylindrical kind of storage wherein we had some kind of location or area on the surface of that drum, and the drum kind of rotates, and then electric signals are passed to that rotational drum. And from there, the data is kind of, or the information is being stored, or it is represented in some form. That is what is a magnetic drum memory. Then came the first commercial version to store data, and this was IBM 350. This was the first random access based magnetic disk storage to store data, and this was pretty huge in size. And then this was transported in some kind of vehicles or even aircrafts. And then this was installed in the basement of some building. And that is where the IBM 350 series came into picture as the first commercial way to store data. And this was sold for a whopping price. The kind of storage that we are seeing is essentially structured storage. And this is where we see RDBMSs and data warehouses, right? This is something that is very important even today. And as people started moving from the magnetic disk based to other kind of storage formats, enterprises also started storing data in some kind of a structured way or in a tabular format. And this is where this became very important. So around 1970 is when DBMS rules were given by EF Cord. Those are famously known as Cord rules as of today. And that is what laid the foundation for RDBMSs and data warehouses and all the kind of databases that came across, especially in the relational side. Right. So RDBMS essentially stands for Relational Database Management Systems. Okay, that is what RDBMS stands for. And we'll look at what RDBMS is, and then we'll move on to why they are still being used and how is that these databases are still relevant today. So we'll try to understand why it is that and why SQL plays an important role for all of these. And then came the period for storing huge amount of analytical based queries. And that is where organizations or enterprises wanted to know, get some kind of information based on the data that is stored. So these systems that store data for a historical purpose were queries can be run in order to, run some kind of decision making, or probably have huge amount of data being stored. In those days, terabytes was still huge. So that terabytes of data was stored in data warehouses. And this was essentially for doing offline kind of processing or offline kind of querying. In such cases, people use a data warehouse. But in real time, let's say we wanted to do it in online mode, where let's say we have a website and we want to log in and then do some kind of a quick form submission so that data is captured somewhere, right? In such kind of online scenarios, RDBMSs were used. So generally, RDBMSs are used for what is called as OLTP. OLTP stands for online transaction processing. So that is where RDBMSs are used, and data warehouses are used essentially for OLAP, online analytical processing. And these two are very important even today. They are still considered very important, and SQL as um, a skill or a language is still very much needed in the industry these days as well. So we have RDBMSs, data warehouses, and then slowly something else came up, which is called as data lake. So data lake, as of today, is capturing all of these. We have RDBMSs, we have data warehouses, and other kind of querying formats of storage. So data lake is representing all of these, and SQL is still the go-to language apart from the other programming languages like Python. Okay. So that is where it still plays a very relevant role for organizations, and especially in the tech industry. This is still very relevant. Okay. So data warehouses, as we said, is used for OLAP, online analytical processing, and RDBMSs are used for online transaction processing. So that would be the difference of why somebody would prefer a data warehouse and why somebody would have an RDBMS for OLTP. Fine. So anything that we want to look for decision making, or we want to generate reports or some kind of analysis, we will perform those on data warehouses, right? We'll run some kind of programs using SQL generally, and then try to retrieve the data and see how that could be done. Okay, so that's about RDBMSs and data warehouses. Next, the storage still started evolving, and then we had CDs, DVDs, and Blu-ray discs. All these kind of different kind of storage mechanisms started evolving, and they are still relevant in the industry. This may not be today as of today, but at one point of time, people used to have a stack of CDs or DVDs containing a lot of information. But today we are having huge variety of storages, right? We can do it in a hard drive, or we can do it in a pen drive, or probably in the cloud, or in some kind of a backup external drive, right? But at some point of time, this is the kind of storage that we had. About GBs of data could be stored on these kind of disks. And Excel is something which is very common that we have. So Excel is a software, right? Essentially to store data in a tabular format. This is also something that started coming up from the Microsoft company, where people started realizing if they wanted to store data nicely represented in a tabular format, Excel is one place that could be stored, right? So we had Excel, and then there are different formats that are supported in Excel now. We can use CSV, TSV, different kind of separators in order to store the data. And this is one way to store the data. Then there was also a period where we had something like about to install a minimal software, probably we used floppy disks. Floppy disks were also something that were used in order to store the data. And this was about MBs of data that was being used. And then came hard disks, right? The hard disks, with the advent of machines, the hard disk became so common that now hard disks are also used as external drives as of today. So this is again something similar to what magnetic drums were there, right? Or IBM 350 that we had seen. The same principles were applied, and now this was packaged and stored nicely in a computer machine. So hard disk again has a similar kind of technology in terms of we have a spindle, and there is a disk area, and there is a head that rotates on this disk area, and certain sectors are created, and then the data is stored onto the disk because of this rotational nature of the pin that is attached to this particular head area, right? It kind of writes the data and reads the data from this disk area. Okay. And then came very handy kind of storage mechanisms, especially memory drives. Probably today we are looking at 64 GB as something which is common, but at some time it was about 1 GB, 2 GB, and slowly it came up to 64 GB, right? This is something most people are aware of. If the disks were not available, probably we would have carried the data in these kind of storage mechanisms, very small little things that could be carried in the pocket. Right. So that's about the evolution of storage. But when we look at data, right, today we have different kinds of data, right? And why are we trying to understand this is because we have different kinds of data and how do we store the data and how do we retrieve that data? For example, if we are looking at a desktop or a laptop, probably if there is some data that we store as files or probably audio files or video files, we know how are we storing them, right? We really do not need any kind of software to represent the data in a perfect structure. We have a folder, we just dump the data into a folder on a drive. And that is what we try to do. But then when we have huge number of parameters, textual data, date, etc., we want to store the names of something and we want to kind of retrieve it and see what the information is associated with something that we want to represent in the real world. Probably these folders and files storage will become too cumbersome and it will lead to a lot of maintenance problems, right? Let's say we want to store the details of students of a particular university, right? And if the moment we start doing it in an Excel sheet or in a particular file, right, it becomes, if it is the date, if the number is less, probably it becomes very easy. But if the number grows, then it might not be so easy. Let's say we want to capture data from 10 or 15 universities, right? And then maintaining that data in an Excel sheet becomes too cumbersome, and also retrieval of data will become not so easy. I mean to say, when you want to search for a particular name from a particular college, that might not be so straightforward as we might think so when we were trying to save it, right? So these are some of the challenges. And also, if you want to edit some details, that might take longer time now. Maybe initially it was easy to add a name, but we want to edit something, it might take a longer time to edit that particular field or a name. So, and also we want to maintain multiple versions. When was a particular change done, or if you want to know how it was being done, where it was stored, probably these are some aspects that might not be so straightforward. Probably this have solutions, but this might not be so straightforward. So these are some of the challenges that we see. And also, if a machine goes down, how do we make sure the data is available, right? So that is something that is also an industry problem. How do we make sure data is made available continuously? So when we look at these kind of things and the kind of data that we deal with, data can be classified into three different categories or three different types. We can classify them in structured data, semi-structured data, and unstructured data, right? Structured data, if we have to define it, it is essentially something that can be presented as rows and columns or in a tabular format. If we can present the data in a tabular format in rows and columns, that would be a structured data. Right, and essentially databases and data warehouses were the places or the softwares where we could have this data represented in a structured format, right? And that is what still in the industry follows also. For structured representation of data, we use databases and data warehouses. And when we say databases, they are RDBMSs, relational database management systems, right? That is what is still being used when we say it is structured. And then we have semi-structured. When we say semi-structured, it is not really structured in nature, but then it still carries some kind of information. Our data can be passed by representing the data in some form. So when we say representing it some form, examples for semi-structured data are essentially JSON and XML. We can have JSON and XML format represented in some format and then passed on over a network, or if you want to use it in a program, we'll be able to do so. That is what is semi-structured. And we'll look at what examples of JSON and XML are, but JSON stands for JavaScript Object Notation. And XML stands for extensible markup language, right? So this is JavaScript object notation. The first letter of each of these words have been taken and formed a JSON. But for XML, it is the second letter that has been considered. So in extensible, it is X that has been taken. And in markup, it is M, and in language, L has been taken. So it is extensible markup language. So we have JSON and extensible markup language as examples for semi-structured data. And for unstructured data, which is really not having any pattern or any kind of representation, that is essentially an unstructured data. So log files, videos, and images would fall under unstructured data. So these are the three types of data that we can come across. And broadly, this is how data is classified in the industry as well. So when we talk about types of data, structured and semi-structured, semi-structured, and unstructured are three types of data that is very important in the industry as well. So how did this begin? When we talk about these three types of data, but also there was something else that also, began moving from one place to another place, in the sense that over a period of time, different technologies came in to store or represent the data that we discussed previously. So when we look at RDBMSs or databases, the first relational model was done in about 1970. And this was done by E.F. Codd. He presented a paper in which relational model was discussed. And that is where the journey of RDBMSs started, right? And then in 1970, late 70s, Oracle started developing RDBMSs. So they started bringing out their own RDBMSs. Oracle started coming up with their own RDBMSs. This was in late 1970s, late 1970s or 1979. The first RDBMSs was already there. And then in 1984-85, Postgres SQL started coming up as another RDBMS, and slowly we had a SQL Server and MySQL coming up in the 90s. And one important thing happened in the late 90s was that Google was formed. Google as a company was formed, and Google essentially was a search engine. So what does a search engine do is it tries to get the data from the internet and present the data with a particular ranking that it searches over the data that it has brought from the internet. So that is what happened. And when the data is brought from websites, right, it is not necessarily in a structured format, right? Data can be in text, there could be images, etc. So all of this data was not in a structured format, and Google started with its own technologies of how to kind of process them. And that is where in 2000s, it came up with what is called as Google Bigtable, and that started with a kind of a database called as NoSQL. NoSQL stands for not only SQL, and SQL stands for Structured Query Language. Right, so we could say 1979 to probably about 2001 or two, we had a period of relational databases and data warehouses. It is not that it is ended, but that is where a lot of research went in, and focus was on databases and data warehouses most of the time. And then from mid 2000s, we had NoSQL databases till the late 2010s. Or the early 2020s. Till then, we had NoSQL databases. And the period that we are in, the research already started essentially for distributed SQL and cloud-based computing services. Right, that is something that has started, and people are focusing on that. And we'll see a lot of these technologies from now in the near future. Doesn't mean that relational databases and NoSQL databases will not be used. They will be still be used, but different kind of databases are coming into the industry, and a lot of research is also being done, right? So that is how RDBMSs started growing, and we'll look at what it means by whether they are still relevant or not. So there has been a ranking that has been done. So we have various popular databases, and about 420 databases are considered. And this particular database, this particular website, which is dbengines.com, ranks the databases based on the usage and popularity, and it has some indices by which it uses to rank them. Okay, so Oracle is the first database with the rank 1. Okay, it's still there. Even in June 22, it was ranked 1. Even 21, it was ranked 1. And then we have MySQL. MySQL is again an open source software that is available from Oracle. It is still ranked 2. And then we have Microsoft SQL Server. This is an RDBMS. This is ranked 3. And then we have Postgres SQL or PostgreSQL. MongoDB is the non-relational database. How do we know? If you look at the database column, the first 4 are still relational databases. And the fifth comes document database. This is a MongoDB. This is a document database. And then Redis is key value pair. IBM DB2 is relational, Elasticsearch is search engine, etc. So there are about different databases here. I have taken only the top 10, and the list is about 400 databases that are used across the industry. So all of these are ranked. So even when we look at top 15, right, 6 to 7 are still relational databases only. Right. So even today, the best databases that are used based on different indices and the score that they come up is still for relational databases. So relational databases are still used widely across the industry, even in 2023, even though we have seen this kind of developing technology, right? But still, RDBMS is still the famous ones, right? Hardly their ranking has changed over a period of an year or two. They are still maintaining their ranks in the top place, right? So that is how RDBMSs are playing an important role. Still, majority of the data that we use is on the structured data, but the amount of data that is being generated is there in semi-structured and unstructured only, right? And that is where we are trying to see how do we kind of store it, and that is where the other kind of databases are needed. Fine. So when we look at these things, it becomes clear that RDBMSs are still important databases to know and to learn about how do we interact with them. And SQL is one language that helps us to interact with them. Probably we can also interact with these databases using Python or other programming languages. But again, they internally use some kind of SQL syntax in order to work with them. So it is better to know what SQL is and to work with it. Right. So I would request you to follow this link, https://dev.mysql.com/download/installer. So this is the place from where you can get the software for MySQL. And it is a installer for Windows, pretty straightforward to install it. And all that we have to do is give a proper usernames and passwords, and we need to remember them because we have to log them, use them in order to log in. Right. So this is the place where we'll be using MySQL to download from. So please take a note of this, and probably if you have not downloaded it, try to download it from this particular URL. Okay, so that is where MySQL will be available, and it could be installed, and it is open source. We can use it without any license, right? So this would be a community edition that we would be using. So we need to have MySQL server up and running for this session so that we can start working with SQL. All right, so that is what would be needed for all of these sessions that we'll be using MySQL for SQL. Okay, so when we started off with this, we saw what was storage and why RDBMSs are still relevant even in 2023 and why it is very important, right? So first thing, let us try to understand what RDBMS means. So RDBMS stands for Relational Database Management Systems, right? What are we trying to store? We are trying to store data in the form of rows and columns, right? And the data that we store is somehow related to each other. That is what we would see. And data is essentially stored in the form of tables. And what is a table? What is a row? What is a column? We'll try to understand as we go further. But then an horizontal representation of the data is nothing but a record or a row. That is what we would be calling as a row. And something that is vertical in nature would be called as a column, right? And the place where the value or the data is stored is called as a cell, right? But how did we come to this place, or what was the fundamental rules that drove how to store data? So these rules were proposed by E.F. Codd in 1979 to 1985. Right, 1979 was the first time the paper was proposed by E.F. Codd, and then the rules were formalized slowly. that any database management system that is to be called as a DBMS or a database management system, it has to follow these 13 rules. And that is what was proposed. And majority of the databases as of today follow about 11 to 12 rules anyways. That is how they follow. And these 13 rules that were proposed were called as CORD rules. Very important rules, and we'll look at them. Right. So before we do that, let's see how the data is stored in a table. So a table would look something like this. This would be our logical representation of the data. Internally, probably it might use some other data structures, and internally it might be stored physically on the drive as files. But for us, when we use some kind of a logical way of representing it, we call that representation as a table. And the table will have rows and columns, right? These are rows, and these horizontal ones that we see are called as rows, and the vertical ones are essentially called as columns. So in order to identify the value, we have something called as name, and these names are nothing but column names. So ID, name, year, subject, and department here is nothing but the column names for the table students, right? So that is what we have here. So we are trying to use the column names and the table names in order to identify it. Okay, so so these are the column names: subject, department, year, name, and ID. These are the column names, and students is the table name. And these things that we see here, these are the rows, and these are the columns, right? And the value where it is present, this is nothing but a cell, right? This is a cell, and the value for this first row with the ID 101 for name is Suraj, right? These are the rows and columns that we have, right? So that is what would be a table. And there are other things that we might have to discuss as we go further. We'll try to understand them as well. How do we identify a row? What would be the unique nature of representing it, etc. So these are some things that we might need as we go further. All right. So, and how are these tables? How do we say something is an RDBMSs, and what should the rules be followed is given by these 13 rules that we have, and these are called as CORD rules. So the first rule, or I would say rule number 0, and the first rule is called as the foundational rule. So whenever we talk about RDBMSs, the foundational rule states that databases have to be managed internally with what are called as relations, or they should have relational capabilities. That is what is the foundational rule. And rule number 1 states that we should have what is called as an information rule. So for a database, if we have to store the data, we need to have tables, and the tables will have rows and columns, and the data will be stored in what is called as a cell. And that is what we have seen previously. The next rule, which is nothing but rule number 2, is called as the guaranteed access rule. The value that is there in a cell should be accessible logically, right? So we should be able to retrieve that particular cell value, any cell value that is available in the database or in a table, right? This one, the atomic value that we are calling is called as datum, right? This is called as datum. What it means is it is inseparable. We cannot separate it. So datum should be, or it must be logically accessible, right? And we can use some kind of tools in order to retrieve them. The next rule, which is essentially the rule number 3, this rule is systematic treatment of null values. So what it means is that null values needs to be represented in a table. And what does that mean? In a database, if we have to represent the null values, they have to be for some kind of data that is either missing, or if the data is not correctly represented. In such cases, we have to represent it as null values. And something which is empty string, or if there is some kind of a blank space, or if the value is not present as empty parenthesis, right, or if it is present as empty parenthesis, these should not be treated as null values. Only if it is missing, or if some kind of inapplicable information is being associated with it, then we can say that it is a null value, right? The next rule that we have is the dynamic active online catalog on the basis of the relational model. What does this mean is that we need to have something called as a logical structure of the database, and it must be stored whenever we want to whenever we want to access it, it must be accessible. And we should know what are the different mappings that are associated to it, right? We'll understand this when we create a table and how are we trying to get a column, right? That is what is referred to this particular rule. And whoever is authorized to log into the database, they should be able to see the objects or the cell values. Once the authentication has been completed, they should be able to view them using some kind of a query line. And that is what is dynamic active online catalog on the basis of relational model. The next rule is the comprehensive data sub-language rule, right? So what it means is that any kind of language that we want to use, we are free to use. And if we are trying to access the database, that language that is being used should be supporting everything that the database is supporting in terms of the relationships, in terms of how are we representing the data, or how do we define certain values, or how do we kind of present the data. All of these should be present in the comprehensive data sublanguage rule, right? That is what is this next rule, right? The next rule is the view updating rule. Now, a view is something where, let's say, an underlying file is modified, right? And then we want to update it. So whatever is being represented at the logical level, that should also represent what is there at the underlying, or the underlying data that is available in the file, right? Any updates that are being done on the underlying file, the view also should have those kind of updates. That is what it means, right? So a table is nothing but a view, and the table represents the data that is present in some kind of a file. So that is what it should be doing. An RDBMS must be doing with respect to the view updating rule. The next rule, the seventh rule, is essentially the relational level operation. What does this mean is that different kind of operations must be supported in the RDBMSs. What are these operations? Insert operation, update operation, delete operation. So either when we are trying to insert too many records, or probably one record, or in multiple tables, or in a single table, all of these operations should be supported at each level, whether it is one record, two records, one table, multiple tables, or at a database level. These kind of operations should be supported at every level. That is what this relational level operation says about. The next rule is the physical data independence rule. Now, what this means is that whenever we are having different kind of data that is being stored and it is being accessed by different application, the data that is stored should be independent of the other data pieces that we are storing in the database, right? That is what is physical data independence means. What does it mean is that, let's say we are having one table stored in one file, probably there is another table stored in another file. So these should be physically independent. We cannot have all of the data mixed up and stored in a single file or probably at a one place. That is what is physical data independence. Similarly, for next rule, which is similar to what we have seen now, we have a next rule which is called as logical data independence rule. Logical data independence rule also states this, that let's say if you are trying to break a particular view or a table into multiple parts, then those tables should also be separate. It should be independent of each other. Nothing should actually come into the other view or in the view that was previously held, right? Once broken, it is means that they are two separate tables and they should be represented like that. So this is what is logical data independence. The next rule is integrity independence rule. So integrity constraints should be stored separately from the applications that are accessing the data. What does integrity constraints mean, and how do we apply them? Is there any kind of rules on the data itself, is something that we'll see as we go further into our SQL sessions, okay? But then but then an RDBMS should also follow this integrity independence rule. Okay, the next rule is the distribution independence. This is the next rule, which is distribution independence in the sense that data could be distributed across network or in multiple places, right? But whoever is using or viewing that data, they should not know where this data is stored. That is what is distribution independence. Probably they are using 2 machines or 3 machines, or probably 2 or 3 hard disks that are interconnected with one another or not on the same machine, right? So whenever the data is distributed like this, the user who is using data should not get even a single hint of where the data is stored, right? That is what is distribution independence. Then we have the non-subversion rule. So what it means is that sometimes there might be more privileges to access the underlying file system of an RDBMS. So when in such a case where the data is accessed at such a level, then the integrity which is being held on that data, that should not be subverted or it should not be changed. Even though data is being accessed, doesn't mean that whatever was represented previously, that can be changed. That should not happen. So these are some of the things that the CORD rule says about. These are about 13 rules, and uh, some of the databases that we have follow 11 to 12 rules that we have here, right? So that is how CORD rules play an important role with respect to RDBMSs, right? The other thing that RDBMSs, or when we talk about structured data, is what is called as ACID properties, right? We came to know about the 13 CORD rules, but then we have something called as ACID properties. What are ACID properties? ACID means A for atomicity, C for consistency, I for isolation, and D for durability. So these are the important characteristics of an RDBMS. Now, what does this mean? What do we mean by atomicity? Atomicity means, let's say we have certain transactions that are being made, and we'll go through what it means as we go further. Let's say we have some kind of a transaction or certain set of statements, right? So let's say we are trying to debit from one account about $500, and we are trying to credit $500 into another account, right? So the entire transaction is about debiting it from one account and crediting it into another account, right? So when the debit happens, this money should go and fall into another account B, right? So this thing should happen completely. It cannot happen like debit has happened, but credit has not happened. That cannot happen. Atomicity means that whenever such a transaction is happening, where debit and credit are happening, both of them should happen. It cannot be only debit happening and credit happening, but then debit does not happen. Let's say credit has happened into one account, but debit has not happened, right? If the transaction has to happen, it has to take place in complete form. Maybe today, because of the growing internet and various other things that are there, we have a distributed databases across different banks. Because of network lag and certain things, maybe this is happening, but even that is also about 1% of chances, right? Very, very little, very, very rare chances. But then with respect to a database, if this is happening from something has been deducted from some place, and it has to be added or credited to some other place, then both of them should happen together or nothing should happen. That is what is atomicity. The next one is consistency. What does consistency state is that consistency states that transaction should happen in such a way that uh, for the definitions of the table or the uh, changes that are expected on certain tables, that have to be happened what was defined previously. Okay, that is what it means when we say consistency. Means, let's say if there is 4 fields, only 4 fields can be accessed, and we can make changes to those 4 fields and probably make changes to a table of another account for those 4 fields only, right? So let's look an example. So let's say we have 2 accounts, A and B, and account A has about $500 and account B has $300, right? So we want to transfer $100 from A and put it into B, right? So amount for A is 500, amount for B is 300. We want to remove 100 from A and put it into B. So after this transaction is completed or $100 have been transferred, A should reflect 400 and B should reflect 400, right? So 500, 300, 500 minus 100, 300 plus 100 in B. right? So 400 should be reflected in A and 400 should be reflected in B, right? And if we sum them up, let's say we sum up these values, account A plus account B. Previously, the previous state was account A plus account B, total amount is $800, right? After this transaction or after this transfer that has taken place, account A is 400, account B is 400. Total amount for account A and account B is still 800. So this reconciliation that we are doing, or this verification that we are doing before and after the transfer, should still maintain or give us the total amount as the same. That is what is expected. Or the predefined state was 800 was there as the total amount. Now it should also be total as 800 because there is no other account involved. Only these two accounts are involved. Fine. So that is what is consistency. They should be consistent. Any predefined values that we are considering or any kind of predictable changes that are being done on table, they have to be consistent. All right. So or the data integrity has to be maintained completely, or it is not cancelled in any partial manner. It should be cancelled completely. That is what it means by consistency. Then we have isolation. Let's say we have multiple accounts A, B, C, D, E. A is doing his own transaction, B is doing own transaction, C, D, and E. Each of these accounts are doing their own transactions. So if they are doing their own transactions without having any dependency on each other, let's say A is doing for A2, B is doing for B2, C is doing it for C2, D is for D2, and E is for E2. So they have their own individual transactions. So these should run concurrently and should be independent of each other. That is what is isolation. They should not be interfering with one another. These transactions should not be interfering with one another. They should be done independently and they should run in a concurrent manner. That is what is isolation. The next is durability. Now, what we mean by durability is, let's say we have transferred $100 from account A and that has been credited into account B. Now, because of some power fluctuations, the machine has gone down. So now we know account A has $300 and account B has $100 more than the previous amount history, right? So now once the power is resumed, it should be in the same state. Data should not be lost, or the transaction that has been done, it should be in the completed state. If it was done, or if the transaction was happening during the power failure, it should revert back to the previous states of account A and account B respectively. Right? So that is what is durability. Right? Any changes that were saved or persisted should reflect back because of any network failures or system failures. It should not sabotage what was done previously. Okay, so that is durability. So these properties need to be present in a RDBMSs, and these properties are called as ACID properties, or atomicity, consistency, isolation, and durability. And these are the 4 properties that are needed. Okay. And when we talk about the way we want to interact with RDBMS, we use what is called as SQL. SQL's full form is structured query language, right? So what do we mean by structured query language is that it is basically a declarative language. What it means is, when we say declarative, we can specify anything that we want in order to retrieve something in, or we want anything that we want to declare and then use it, we can start using it, right? That is what is a declarative way of retrieving data using SQL. And that is why SQL is called as a declarative language. Okay. We can specify what we want to retrieve, and we can also specify what needs to be modified or updated, right? That is what is SQL. It is a declarative language. And SQL follows what is called as ANSI standards. SQL follows what is called as ANSI standards. ANSI stands for American National Standards Institute. Majority of the databases comply by the ANSI standards. That is why we see the syntax being same, more or less the same across different databases. Very small changes here and there. That is done because of their proprietary nature. That is what is there. But once we know SQL, this is almost the same across different databases. Right. So why should we learn SQL, or why is SQL important? Point number 1, as I said, if you want to deal with data, right? We do not want to compute. We want to deal with data. We want to see quickly, or we want to do some kind of analysis. Apart from programming language, we can deal with databases using SQL, and majority of the analysts across the industry use SQL as the standard language to interact with it, right? Majority of the SQL standards or SQL analysts or developers, even today data analysts still use SQL as the preferred choice of language for interacting with the databases, and then probably then visualize it, right? And where it is used in every data data domain, like data warehousing, data quality, data integration, business intelligence, data science, machine learning. Some of the tools that we see today are using SQL as well, right? So SQL has become one of the de facto standard for or kind of interfacing with a database or with different domains of data. Okay, so that is where SQL has become very important. And when we talk about SQL, SQL can be categorized based on the different kind of statements that we use. So what are the different statements that we have? There are different kind of statements. The first statements that we'll come across is called as DML, or data manipulation language, right? So select is the statement that helps us to retrieve the data from a table, and we can use certain conditions. We'll see what it means. But in order to retrieve or view the data, we use select, and it is a DML statement. If you want to add rows to an existing table, right, we use insert. This is also a DML statement. In order to change or modify, we use update. In order to remove records from a table, we use delete, right? And this could be again specified based on certain conditions. That is what we can use delete for. All of these are DML statements. Then we have what is called as DDL, or data definition language statements. Data definition language statements are create, alter, drop, and truncate. These are the major DDL statements. Create is used for creating a new object in the database. It could be a database, it could be a table, it could be a view, index, or different kind of objects like functions, etc. Right? So these are different kind of objects that could be created within a database, and for that we use create. If you want to modify an existing object, we use alter, right? That is where alter would be helpful, and it is also one of the DDL statement. If there is an already existing object like table or view, and we want to remove it or we want to delete it, then we use drop. If you want to remove all the data from an existing table, but still maintain the table as it is without deleting the table or its definition, then we use truncate. Truncate only removes the data. It does not remove the table itself. Okay, all the data that is available in the table is removed. That is what is truncate. Now, there are different users in the database also. Just like we have users for a machine, users for a particular login system, etc. For a database also, we'll have different users. And to provide users with certain privileges, or we want to remove certain privileges, we use what is called as the DCL, or data control language, right? And grant and revoke are two statements that could be used for granting privileges to the users in a database using grant, or if you want to remove the permissions or the privileges that are there on the users or on the roles that are there in the database, we use revoke. If you want to kind of save certain state of data with respect to certain statements, then in such cases, we use TCL, which is called as transaction control language, right? Previously, data control language was with respect to the roles, but similarly, if you want to maintain certain states with respect to the transactions that are taking place in the database, we use TCL, or transaction control language. Commit helps us to save the changes that are being made permanently. That is what commit helps us to do. Rollback, it reverts back to the previous state before some kind of save is happening. Right? That is what rollback. It kind of reverts back to the previous. Then we have save point. Save point is essentially, let's say we are trying to do a transaction. Before it can be rolled back, we want to save it somewhere, and that is where we want to, that is the point where we want to save it. That particular point becomes a save point, right? or it is essentially whenever we want to roll back to a particular point. Let's say this is the point that we want to roll back. Then that also can be defined as a save point. Let's say last two updates were done and those two updates we want to reflect back. That is what is a save point. So this is essentially TCL, transaction control language. So we have commit, rollback, and save point. These are the statements that come under TCL or transaction control language. Okay. So before we start executing SQL on MySQL, MySQL comes up something like this. It is basically a server that runs on our machine. So we'll have a MySQL server. And inside this MySQL server, we as a user, if we want to start using it, so we have to create that user when we install it. One user would be created and multiple other users can also be created when we start installing it. So we have to authenticate ourselves in order to log into MySQL. So we have to provide a username and a password, and then we'll be able to log into MySQL. So once we log into MySQL, it is basically a server and it will have other databases or other schemas. So at the top level, we'll have the MySQL server. Inside the MySQL server, we'll have various databases. And each database will have its own set of objects, right? Tables will belong to one database. If there are other tables, that might belong to another database or schema. A database or a schema is the same. At the top level, we have the server, then we have the database, then we have the table, then we'll have rows and columns, right? That is how the objects will be created. So most important is that we need to have MySQL installed. It is a software that will be installed. And once the MySQL is installed, we can log into this MySQL by providing a username and password. Once we provide the username and password, we will be able to see what is there in the server or what are the other databases that are there in the server, right? So that is what we have. So what we'll do is we'll try to see MySQL. Hope you're able to see the MySQL workbench, right? Once you install MySQL server, we can access MySQL server using this UI. MySQL Workbench is what is called as a graphical user interface. That will be available from the Windows Start page, and there you can find MySQL Workbench. Once you install the MySQL server, we can log into MySQL using MySQL Workbench. So this is the UI of MySQL Workbench. So tomorrow we'll get started with MySQL SQL queries using MySQL Workbench. So request you all to have MySQL installed on your machines. Okay. So any questions for today with what we have done today? Okay. If there are no questions, then what we'll do is we'll meet tomorrow, have MySQL installed, and we'll start running SQL queries using the MySQL Workbench. All right. Till then, thank you so much. Good night and goodbye.